Today we're going to talk about a completely different kind of function called a polar function. It is very, very different from what we're used to, which are called rectangular functions with x and y axes. Instead, with polar graphing, we don't use x and y, we use r and theta. So the r stands for radius, is instead of just a standard position in the x distance, like a horizontal distance like the x value, the r is the distance from the pole. The pole is another name for the origin. It's that center right there. And the theta value isn't actually measuring a distance at all. It's not like the y value, which is measuring a vertical distance like that. The theta is measuring the angle of rotation around in a circle like that. It'll make a lot more sense in just a second after we look at an example. So let's try and graph the point 1 pi over 3. What that means is that the radius, so the distance from the pole, is 1, and the angle of rotation is pi over 3. So the point lands right here. Now, when we graph this, we don't show the arrows here. I just made those to show you how we got to this spot. This point right here is 1 comma pi over 3. So although it's very different from what we're used to, it's not that complicated. Again, r theta is just the distance from the pole and the angle of rotation. Graph a couple more points. You can certainly have a negative r. So we'll graph the point negative 2 pi over 2. In that case, when it's negative 2 pi over 2, you imagine yourself going backwards 2 units and then rotating pi over 2 from there. Now, it's important to remember that when you rotate pi over 2, that's always in a counterclockwise direction. When we talk about pi over 2, just like in your trig and pre-calc classes, you learned that angles are discussed in a counterclockwise way. So pi over 2 from there would be that far, which would land you right here. So that point is negative 2 comma pi over 2. If you prefer, you can also think about it as doing the pi over 2 direction, the rotation first. Think of it almost like a speedometer or something in a car where there's like a needle that's going around, and it's pointing up in this direction, and then the radius of backwards 2 just means that from there we go down 2 units, or backwards 2. I personally prefer thinking of the direction first, but if you prefer thinking of I prefer thinking of the radius first and then thinking of the direction. If you prefer it the other way around, that's fine too. We can look at another couple of examples here. You can have a negative degree also. So the point, let's go to negative 3 pi over 4 would be a radius of 2. And then rotating negative 3 pi over 4 would take us back to here. So this point right back here is 2 negative 3 pi over 4. I want you to notice that that is the same thing as pi over 4, as negative 2 pi over 4. which would mean going backwards 2, and then forwards pi over 4 radians. That would land in the same spot. So any polar coordinate can actually be written in multiple ways. Okay, so hopefully now you understand a little bit about how polar coordinates are written. When you see this when you see coordinates written like that, you're told that it's r theta. Make sure you understand that this is not x and y, but r and theta. We'll graph it differently. Okay. Important to point out, though, that you can, of course, still think of the coordinates, the xy coordinates of a polar point also. So if we have the point, let's say, 4 pi over 6. That's 4 is the radius out to here, and pi over 6 brings us up to here. If I wanted to convert that to rectangular coordinates, I can. It's actually very easy, but it's an important thing that comes up a lot. You have to be able to do this. The x value of any polar coordinate, so if the polar coordinate is r theta, the x value is r times the cosine of theta. The y value is r times the sine of theta, which makes a whole lot of sense because if you imagine the x and the y coordinates here, remember the radius is the distance straight back to the pole, and the theta is this angle right here. So basic trig is that the sine of theta is equal to the opposite over the hypotenuse, and that's why x equals r sine theta makes so much sense. So for this coordinate that we have here, this 4 comma pi over 6, the x value is 4 times the cosine of pi over 6, which is 4 times root 3 over 2, which is 2 root 3. And then the y value would be equal to r times the sine of theta, which is 4 times 1/2, which is just 2. So the rectangular coordinate at that spot, I should say rectangular coordinates, are 2 root 3, comma 2. So that is the rectangular coordinate at that point. The last thing to talk about with these polar graphs, or polar functions, are actually functions themselves. So when we graph a polar function, it is defined as the radius is a function of the angle. If we have a constant, like just r equals 1, this is a bit of an odd case. But what this means is that the radius is always 1. It doesn't matter what the angle is. Well, that means that when the angle is 0, the radius is 1. When the angle is pi over 6, the radius is 1. When the angle is pi over 4, or pi over 3, or pi over 2, or 2 pi over 3, the radius is still 1. Saying that the radius is 1 no matter what just means that it is this circle. So r equals 1 is a circle. Okay, but normally we have functions where the radius actually changes as theta changes. So here r equals theta. What that means is that when theta is 0, so when I'm facing straight into that direction, the radius will be 0. So I will actually start right here at the pole. As the radius gets bigger, as the theta gets bigger, so as I start rotating around, the radius will also slowly get bigger. I'm going to scale this as, I'll call that 1. So by the time the radius is pi over 3, which is out here in this direction, that's pi over 3. Pi over 3 is 3.14 divided by 3 is just a tiny bit more than 1. So the radius has grown. By the time it gets to pi over 2, which is about 1.7, we're up here. By the time we get to pi, so by the time we're facing back here, the radius is all the way out here at 3. And so this will keep going and just make a bigger and bigger spiral as we go. I didn't draw that very well. One thing that's worth pointing out is you can graph these on Desmos also. If you r equals theta, here's the spiral. Also on Desmos, you can change the graph settings. This little option right here changes it to polar mode. So you can see as the radius gets bigger, the spiral keeps going up. Quick look at one or two other functions. So this one, r equals sine of theta. What's going to happen here, because sine is a periodic function, it gets bigger and smaller and bigger and smaller, going between 1 and -1, our, unlike the one we graphed up here, where the graph just keeps getting bigger and bigger, this one will actually form a repetitive cycle. So let's take a look at what it would be. When theta is 0, sine of theta is also 0. So we start at the pole again. But as theta grows, so pi over 6, sine is 1/2. So by the time we get to pi over 6, the sine is 1/2, which is actually not there, sorry. 1/2 is right here. By the time theta is pi over 2, sine is 1. So it has grown. And then it'll start to shrink again. So at 5 pi over 6, theta is 1/2 again. So 5 pi over 6, that's in this direction. Theta is back down at 1/2. And by the time theta gets to pi, the radius, is back down to 0. Now that's not quite as round as it should be, but that's actually a perfect circle. If I were to keep going when theta is, let's say, 7 pi over 6, that's facing in this direction, the radius is actually -1/2. So facing in this direction, but going backwards 1/2, would land me right there again. In the entire third and fourth quadrants, since the radius is negative, what I'm going to be doing is cycling back over this same space again. So I'm just going to keep repeating that circle over and over and over again. So this circle is the graph of r equals sine theta. To do a slightly more complicated one, like r equals 4 minus sine theta, there are a couple of ways to approach it. One is we could just do what I just did, which is make a table for different values of theta and the r that goes with it. So when theta equals 0, 4 minus the sine of 0 is 4. When theta equals pi over 2, 4 minus the sine of pi over 2, which is 1, is 3. So we start at 4, we get as low as 3, because we're subtracting 1, and then by the time we get back to pi, we're back up at 4 again. Along the way, if you wanted to, sine of pi over 6, so pi over 6 is this direction, that would be 4 minus 1/2, which is 3.5, so we would be here. And you can see it's not quite a circle because it's a little bit flatter on top. I didn't draw that so well. But if we keep going to the bottom, so 3 pi over 2 heading through the third quadrant, now 4 minus the sine of 3 pi over 2 is 4 minus -1. That gets as big as 5. So you'll see that it's not really going to be a circle because it's kind of bottom heavy. Maybe I didn't draw that as evenly as I could have. But if we take a look at the graph of it here, r equals 4 minus sine of theta, you can see it's kind of like a circle, but a little bit bottom heavy. It's not quite even. It's a little bit flatter up here and a little bit wider down here. Okay. We will continue to look at more of these graphs in our next class, and what we're going to be doing over the next couple of classes is talking about the calculus of these graphs. How is the graph changing as theta goes around.